Now let's talk about the limit of a two-input variable function, z equals f of xy. The notation looks much the same. We say the limit as xy approaches ab of f of xy equals L. So it looks much the same, this notation. All right. So what does it mean? Well, informally, it means as x and y, domain values of f of xy, get closer and closer to AB, then eventually the f of xy values will get closer and closer to L, which would be a height value of a value on the z-axis, maybe right here. So let's draw the domain of f to get started to help us understand what this really means and to help make a more rigorous epsilon delta definition. Let's draw the domain. The domain of f of xy might be the inside of this blob right here. Domain, D for domain. And the point AB, let's say for the sake of argument, actually let me put it right there. Let's say that's the point AB. So that right there is the point AB. Then let's pick an epsilon and make an interval, an epsilon interval surrounding L, so that this upper bound or upper endpoint is L plus epsilon, and this lower bound is L minus epsilon. Look familiar? Okay. Then in the more formal definition of limit, we're going to say this. For any epsilon bigger than 0, we should be able to come up with a delta bigger than 0, so that if xy is within delta of AB, f of xy will be within epsilon of L. F of xy will be in this interval, if this limit is to exist, that is. So then, can I create an interval here? No. A delta interval won't work here, but I can create a disk, a delta disk around AB. In other words, I'll surround AB with an open disk of radius delta. So this radius right here is delta. And the idea is going to be that, oh, you pick an x value in here, then, sorry, not an x value, but an xy value in here, then f of xy will be guaranteed to be in here. Will be guaranteed to be within epsilon units of L. So let me say that again to be clear. Given an epsilon bigger than 0, if this limit is to exist, then there should be a delta greater than 0, such that if I pick an xy within this delta disk, within delta units of AB, then f of xy will be within epsilon units of L. That's, again, if this limit is to exist. Now, notice, one other thing you should notice from this picture is xy can approach AB from any direction, from here, from here, from here. So it's no longer the left and right directions. So let's show that this limit doesn't exist. I'm going to take two paths to 0, 0. So imagine approaching, you're in the xy plane, you're flat, you're a two-dimensional point in the xy plane, and you're approaching 0, 0. One direction you could approach is along the line y equals x. So one path you could take to 0, 0 is the path on the line y equals x. And if that's the case, then this limit changes. This guy right here changes to x. And so we get the limit of xy, I'm sorry, the limit of 2xy divided by 2x squared plus y squared, rather. As xy approaches 0, 0, this limit becomes the limit as xx approaches 0, 0. And that changes this numerator to 2 times x, or 2x squared, and this denominator to 2x squared plus another x squared, because again, y is equal to x, which is 3x squared. And we have this sort of cancellation. Keep in mind, we never allow both coordinates to become 0, 0. So we don't get a division by 0 there. We get 2/3 essentially. You know, and that's with the caveat that x, y is never actually, they're never both equal to 0, right? Okay, so that's one limit value on one path. Now, let's take the path, how about y equals 0? Which means the above limit becomes the limit as x0 approaches 0, 0 of 2x times, well, okay, if we think about it, if we plug in 0 here for y, we get 2x times 0 over 2x squared plus 0 squared. 2x squared times 0 over 2x squared plus 0 squared, which is just the limit as x0 approaches 0, 0 of, okay, you get 0 in the numerator divided by 2x squared, which is just equal to 0 as long as, you know, x doesn't equal 0, which is the same thing as saying as long as both x and y don't equal 0, 0. So we get two different limit values for two different paths to the point 0, 0 in the xy plane. So we could say this. So two paths to 0, 0 yield two different limiting values. I'll say two different values for the limit. Which means that original limit does not exist. D and E for does not exist. Now keep in mind, you can only use this technique to show that a limit does not exist. You can never use it to show that a limit does exist. Because even if you get the same limiting value on 2 or 3 or a million different paths, you have to show that it's the same on all paths. So you can't use this technique to show that a limit does exist, only that it doesn't. Let's evaluate the limit of x squared minus y squared divided by the quantity x plus y as xy approaches 0, 0. It's a nice continuous function, x squared minus y squared divided by x plus y, nice continuous function. It's a ratio of two polynomials, which is also called a rational function. And rational functions are continuous on their domains, but the problem is 0, 0 is not in the domain of this function. So what do we do? Well, we're going to use a trick that you learned back in Calculus 1. This limit, okay, I'm just recopying this first part, and then I'm going to factor the numerator so that we have x plus y. It's the difference of two squares up here. So I'll factor it as the quantity x plus y times the quantity x minus y. And then we can divide out the offending factor. And we're left with the limit xy approaches 0, 0 of x minus y. So this limit is equal to the original limit as long as x plus y, x plus y does not equal 0. Now, that's the same thing as saying, so if you look at this, it's saying x plus y does not equal 0. It's the same thing as saying y equals, say, negative x. This line is not in the domain of the function we're taking the limit of. But that's okay, because we don't let x, y approach 0, 0 from values of x and y that aren't in the domain. So everything's fine. This limit is equal to this limit as long as we're in the domain of the original function, x squared minus y squared divided by x plus y. So now that we've established that, we can just use direct substitution. Plug in 0 for x, 0 for y, and we get 0 minus 0. Doesn't cause a problem like division by 0 anymore. We just get a limit value of 0.
Let's go ahead and find the 4 partial derivatives. Of this function, z equals 2x e to the y minus 3y e to the negative x. In the process, I think we'll observe that last theorem. We call these the mixed partials. So you might hear somebody say the mixed partials are equal. So you can't say like f sub xx equals f sub yy. That won't necessarily be true, but the mixed partials are equal. So let's see if we can observe that by taking the 4 partial derivatives here. And this gives us a little bit of practice. So help me out, you guys. What would z sub x, the partial of z with respect to x, be? Term by term, right? 2e to the y. You hold the e to the y constant when you're taking the derivative with respect to x. Minus, well, what would it actually be? So for the second term, the only thing that's a variable is the negative x in the exponent of e, right? So it'd be plus 3y e to the negative x, right? You take the derivative of e to the negative x with respect to x, you get e to the negative x times negative 1. So that minus becomes a plus. Does that make sense to you? Okay, let's take, I don't know, z sub xx. What does that get you? What's the derivative of 2e to the y with respect to x? So I'm just taking the derivative of the thing I just found. That's what z xx means. It's the second derivative of z, both with respect to x. Both derivatives were with respect to x. So just take the derivative of what we just found. What does that give you? 0 for this guy, right? So I won't even mention it. And then what's the derivative of 3y e to the negative x? Negative 3y e to the negative x. Because 3y is a constant, so you're just taking the derivative of e to the negative x. By chain rule, that negative comes out front, right? Okay, so over here, let's take, you know, we could continue on here. Let's do the mixed partial now. Z sub xy. So now wait, to get z sub xy, you have to go back up and look at the first derivative with respect to x, right? And then take the derivative of that with respect to y. Okay, so term by term, what's the derivative of 2e to the y with respect to y? Just 2e to the y, right? E to the y is its own derivative with respect to y. And what's the derivative of 3y e to the negative x with respect to just y? 3e to the negative x. Okay. Now over here, let's start with the only kind we haven't found is now when you take the derivative with respect to y first. So go back. What's the derivative with respect to y? 2x e to the y. That's a good start. 2x e to the y minus 3e to the negative x. Now let's do the second derivative with respect to y. So just take what we just had and take its derivative with respect to y. What would that be? 2x just e to the y. Negative 3 e to the minus x with respect to y is a constant, so its derivative is 0. So notice z sub xx, z sub yy not equal, right? But now let's take z sub yx and see what we get. So we have to go back and look at the first one, right? And take the derivative of z sub y with respect to x now. That's what the notation means. And what do you get? Okay, take the derivative of the first term with respect to x. Everything else is a constant, so you just get 2e to the y. Take the derivative of the second one with respect to x. You get plus 3e to the negative x, don't you? Notice that that the mixed partial of z with respect to x first and then y is equal to the mixed partial with respect to y first and then x. They're the same. So I'll just say note. And it'll turn out to be true. As long as those mixed partials are continuous, it'll turn out to be true.